most of you were just enrolled and registered last week. And because of that, we are very behind, the university is very behind on all of this. So there's a few issues that I will handle, don't worry about that. We're still trying to register a few of you that got dropped. I believe there were 6 of you that got dropped. We put in the request yesterday to register you, and I haven't received an email yet, so I'm hoping you'll be registered by today. If you get an email, I'll come back around lunchtime and talk to you more about that. Okay. If you haven't paid or if there's still some fees, what we've been told is that you please pay everything up front, and then we'll go ahead and reimburse you on the back end. So it'll take 2 weeks to get you reimbursed, but what the university wants to see is that the fees are, or the balance is completely zeroed out. We're going to go back in, we have a list. If you send me an email, I have a list of what kind of late fees you have, and we're tracking that. We're going to do it all at once to get you reimbursed.
I tried to pay yesterday. They said you can't pay.
You should be able to pay online. Yeah, because now you would have to go to the cashier.
Balance shows like $50, so the rest of the money are moved away.
So you only have a $50 balance now?
Yeah, I have a $50 balance and I'm dropping. Late fee for the health is way.
Right. So we're going to waive that, but they should have let you pay that online. So,
No, it just says the only balance you have $50 for the late fee, nothing else. And I have a check, I want to go to the office today. The registrar,
cashier card?
student service.
Yeah. So if you have to email me with late fees that you have, I don't know if you go ahead and email me or let me know. Let's do it at lunch. I'm reading this paper. Tell me what late fees you have and the cost, and I'll just track all of that. Any other general student affairs, university questions? I know there's some email questions.
That's what I was going to ask you.
Okay. So email, we're still, some people have, we're able to get it set up. Others, we're able to get it set up but still can't log in. And then others don't have it set up at all. So that is something that you guys need to do on your own. That's what we were told. We can send you the links. I know a few of you, Jessica, did it end up working out? Okay, so I know for Jessie, we set it up. She set up the password, but it took maybe 24 hours to actually work or so. Yeah, maybe a little longer. So even though we were able to set it up, you were able to set up your email, you weren't able to log in right away. For whatever reason, I'm not sure how the university works. That's but your question.
Yeah, I was able to log in, I've got this 267 username. Is that what I'm supposed to have?
No, so that is the course username. You should have your own at UCSD that you can
I
use.
don't.
Okay.
Is there someone supposed to copy for that?
Yeah, so we'll email you the link that we sent to Jessie. That seems to work. So that's how you set it up, right? Yeah. So we'll just send that to the whole class.
Okay.
And then at the break, back at the break, if there are any of these questions still lingering, we can maybe bring a laptop and try to do that also. Yeah.
Forwarding email link, that was in the email.
Yes.
It doesn't work, so, have you experienced it? It's like,
The link critical?
yeah, once the link.
Okay. Did anybody else have issues with that link? The forwarding email link?
I tried it.
It didn't work either?
It wouldn't accept the forward that I would do. Then after I thought about it, I thought, you know what, I really don't want all that, you know.
Sure. Yeah, let me check. Let me double check this also. Yeah. So we'll come back at the break also with other questions. Looks like we're missing 4.
I know one related.
Okay. So any other questions, please feel free to write them down, think about it, we'll come back at the break. We'll be here at lunch also. I know there's 2 breaks before lunch. You know, we're gonna have the full lunch set up right outside, with drinks at 12. Well, lunch is at 12:30.
Yes.
It'll be set up a little bit beforehand, just in case you fell short.
No, we won't.
Second floor. Right when you get out of the elevator, take a left, you'll see the big ceiling there sign. Any other questions? All right, thank you.
So notice that there's no coffee outside. So Eric, get coffee next time. I think it's good to have a little break. Typically an hour and a half is very long lecture. So about 40 minutes, I take like 3-minute break. You can stretch a little bit, and then have coffee in the field also. So get coffee outside. Okay, good. So who did not attend the orientation? The audio for it. So now let's go straight to the report. So here's the first homework. Okay. So the way it works is that every homework has problem set and MATLAB problem, and also discussion, as well as MATLAB exercise. So this MATLAB here in the homework section is for your own to do. The MATLAB base down here is where we will discuss the solution during the MATLAB in the afternoon. Okay? And the discussion problem here is also where we will discuss the solution as well in the discussion section. Lujan, it's recently still too low. So maybe 265 or 68. And I know that there's a big fan here. Like it's loud here. So is it okay to hear me out there? Good. Okay, so take a look at the homework. So the way it works is, the second homework, I will have it ready online next Friday. There's no class next Friday, but I have it online next Friday, so that you can actually do all the discussion before you come. So, okay? So basically, post it a week before, you actually have time to work on it.
So is there a web page for the class, or are you going to be all this class?
Web page for the class, Jason?
It's at ted.ucsd.edu.
Ted, UCSD, EDU, and there's a WES 267 link.
Right, yes.
Yes. So this is accessed from your Triton link?
Right.
Or, yeah.
So use the same account number and password for your UCSD.
So if you have a UCSD email, your username and password that you use will be able to access this website. Okay? But if you have difficulty of accessing the website, we can also send you the solution by email as well. All right. So I sent out a questionnaire, I think a while back, and the variations of background is huge. Okay? So some have taken DSP very recently, some have taken DSP in the grad program, some have not even taken any background material. So what I'm going to do the first hour and a half is maybe we spend a little bit more in the second half. They still review what you're supposed to know. Okay? And then we'll discuss the new material afterward. So in this class, we mostly talking about discrete time, signal, system. So let's talk about signal first. What is the difference between discrete time signal and continuous time signal?
Continuous time is on all the
All time. And discrete time only defined on integer grid. Right? So discrete time, we will have x of n or I, j, k, l, m. Those are the only defined on discrete time. So, an example we can use is maybe at time 0 is 1, at time 1 is 2, at time 2 is minus 1. This could be an example of a discrete time signal, right? It's only defined at the discrete point. Now, we'll talk about how to interpolate later on, how to generate point in the middle, right? And that depends on what process you can use. You can do averaging, you can do more sophisticated algorithms. Okay. What are the fundamental signals in discrete time system? What are the fundamental signals that you normally work with? Impulses. So the signal that we should know or we normally use are impulse. And how do we define impulse sequence? It could be 1 at time 0 and 0 elsewhere. Right, that's the impulse. Now this is useful because I can write any discrete time signal in terms of combination of impulses and shift. Right? So can you tell me how to write x band in terms of impulses? What could be that sample right there? It's delta n, right? This will be delta n. This will be delta n, right? Plus, how do I represent that pulse right there? That sample. 2 times delta n shift to the right. So how do you say shift to the right in terms of obviously, yes?
Subtract 1.
Subtract 1, so n minus 1. So minus shift to the right plus shift to the left. Okay? And then this could be minus delta n minus 2. Right? So in general, any signal in discrete time, I can write it in terms of weighted sum. Weighted sum of delta function and shifted. So in general, I can write x of n in terms of summation, right, in k of shifted delta function. And the weight will be the value of x at k. Right? And the rate of k is arbitrary. Yeah, just put k like this, so it's mean, minus 3 to 3. Is that clear? So just by using the delta function, I can represent any signal in this time system as a linear combination of shifted impulses. And we'll use this later on to derive more interesting results. Okay? This is one of the things that we should remember. Yes?
So x of k is the amplitude of...
Yeah, just the value at time k. Yes?
Why would you multiply by the impulse function? Because it seems like x of n would be just x of k. X of n is x of k.
This is just a value. X of k is x of n at time k. So here is x of 0, right, time delta, x of 1 times delta, x of 2 times delta. So this is just a weight, just a scalar. X of n here, right? N over minus infinity to infinity. So n here is the index of the sequence. X of k here is just a value. Scalar.
It's always going to multiply by exactly 1 again.
Yeah, so the thing here is that this is always 0,
Yeah.
right? So we only pick out whatever it takes. Okay? Okay, so what are the fundamental signals we have? Impulse and then step. Okay, so unit step. And the way we define this step is 1, right, so on. exponential. Okay? We'll use a lot of exponential in this class. Something like a to the n. Right? A can be arbitrary. So a can be a complex number. And a complex number I can write it in terms of the magnitude, called r, and the phase, because e to the j omega to the n. It has to be an arbitrary or a general exponential. Okay, and later on you'll see that the exponential will be associated with whole of the system. All right. Good. So those are basically, fundamental signal that we should know. Let's look at system. So here is the general way of representing system. It's a mapping between input and output. Give me a few examples. So let me take four examples. Give me an example of system. Y of n equal to x of n. I don't know what equal to means yet. So now let's look at the relationship between output and input. Something. Okay, so that's 2, right? That's a fact. That's fine. That's a scalar. Amplify the input. That's fine. A bit more complicated. How about shift? Okay, so 2x of n minus 1 plus 3. That's okay. I take the past input. That's what it means, right? Take the past input, scale by 2, and add it to 3. That's fine. We have one that is a little bit more interesting to look at.
Negative operator. Negative operator.
Minus is okay? But that's this case, right?
You use exponential as well.
Okay, so what do I x squared? X squared and let's look at the last one. How about x of 2n? So here are 4 examples. Okay, let's call them system A, B, C, and D. That's one more. Okay? How about y of n equal to y of n minus 1 plus x of n. So the current output is a past output added to the current input. What is that? What is this? How do I? It's the special name of what is this? Yeah, or accumulated. Right. It's accumulated. Yeah, it's accumulated. Okay? So this is a phi system. And what are the properties that you remember? When we talk about systems, we have certain properties that we want to impose in the system to make life easier for us. Right? So, do you remember any properties? For P1, property 1. What's the first one we want for a system? Linearity. So, we normally talk about whether the system is linear or not. And how do I check or verify a system is linear or not? Scale and superimpose. This means that if I have x1, y1, x2, and y2, those are the corresponding input-output pairs. If it's linear, I can take combination of this input. Right? And let's say if I have a1, x1, a2, x2, if it's linear, what could be the output? will be the corresponding weighted of the input. A1, Y1, A2, Y2. And why is this useful? Why is linear useful? Because, yeah.
But it allows you to get the output given one input.
Right. So you can have fundamental signal here. And if you know how they behave, you can predict or you can compute the output. So, for example, this would be sinusoidal, right, which you can build. You can have a generator, you can have different sinusoidal. If you can measure the frequency or the response of the system for every sinusoidal, and if the system is linear, basically done, right? Because basically, my signal coming in, it's a bunch of sinusoidal doing Fourier series, and I know how to find the output. Okay, so it's very, very useful. I'm using the column now. Okay, P2. Yes.
So only because why in a system do that exactly?
Okay, that's good. So let's go here and figure out which one here is linear. All but C. Okay. Let's go step by step, right? Is system A linear? Okay, so this is P1, okay? P1. Let me use P1. Is it linear? Yes?
Yes.
You sure?
Only as it is.
It has memory, so it's the previous sample that it comes out, not the current. So if you try to apply those criteria, I don't know how you apply them because it's the previous sample that determines the next output, not the current sample.
But memory doesn't preclude it from being linear. Right? So why is not linear? Or is it linear? Who thinks linear? That's number 4. Okay, good. So we have 2 volts for linear, 4 volts linear. Who thinks it's not linear? 3 volts, 4 volts. Oh, come on. 5 volts. Good. So for those who are say it's not linear, why is it not linear? Let's see what we do about it. You're the last one to raise your hand. So.
Wrap it out, but it doesn't look like it would be the same on both sides or mirror.
Okay, so let's go through this. Okay, let's test it. Okay, system A, right? What could be the output? If you put X1, what's the output system A? 2, sorry, this one, C. 2, X1, and minus 1. 3. Right? And this one will be 2, x2 and minus 1 plus 3. Okay? I'm going to just make it simple. Just add. Right? And just add them together. This is, we call this is x3. I'm just constructing another signal, which is the sum of these 2 signals, and go that into x3. What will be the output? Y3 will be 2 x3 of n minus 1 plus 3. Right? And this is 2 x1 n minus 1 plus 2 x2 of n minus 1 plus 3. Right? If it's linear, if system B is linear, be the output? What do we have? This one? No. The sum of y1 and y2. Let's back it, right? x1 feed into the system B, give me y1 equal to 2x1 minus 1 plus 3. x2 feed into system B, give me y2 with x 2x2 and minus 1 plus 3. I construct a new signal. I call x3, which is the sum of two signals, x1 and x2. Okay? I don't care about linearity right now. Just feed that one, the new signal x3, into the system. What do I get? I get this. Right? Now, if it were linear, without feeding into the system at all, what is the output? Be the sum of y1 and y2. Right? If it's linear, based on the definition of linearity, the output will be the sum of the two outputs. It will be y1 plus y2, which is what? 6 here, right? 2x1, 2x2, 6, 3 and 3. But this is not linear. This is descriptive data. Right? So if you have a shift, a scale like this, it's not linear. But it's not linear. So P1 is not linear. How about C? It's not linear, right? It's square. How about this guy? Can you describe for me this system? Compression time is decimate. Right, throw away all the odd samples. Take x0 coming in here, you have y0. x1 going to here, this got pick up. x2 got pick up to y1, so on. So it's picking up all the even sample of the input. Or throw away all the odd sample. This is decimation. Right? You decimate the input. Okay? So is it linear? No? Why not? You're shaking your hand. Is down sample and throw away information the same way, independent of input. Right? So still linear. You know, you think about it, right? Y1 will be x1 of 2n. Okay, and so on. So the way to pick out or retain the sample is exactly the same for both entities. So you can show this is linear. So think about it. If you're not convinced, then see me or TA, during the break. We can go more detail. And this one is linear as well. Okay? So next property, P2. What would be another property that makes our life easier? Yes?
Sorry, can you go back to E? Why is that linear if there's a time shift?
Time shift doesn't do anything to the, remember here? A time shift as well. If this not a 3 here, it will be linear. The time shift doesn't change linearity. Okay, what would be another property that we want in our system? Suppose I have a system. In the morning I turn it on, it behaves this way. In the afternoon I turn it on, it behaves a different way. At night, different way. What is the system called? Time variant. It's a nightmare, right? it's very hard to work with. You don't want a system that depends on where you turn on the time. So a good property to have is time what? Invariant. So thing to remember in time invariant is it's independent of when you turn on the system. Right? That's just basically an intuitive way to remember. It does not depend on when you turn on the system. So how do I describe it in equations or block diagram or formula?
Time shift with the input, because there's one time shift.
Right. So at time 0 I turn it on, it looks like a sine wave. At time 5 I turn it on, it should look like a sine wave. So the same as taking the original sine wave and shift it by 5. So the way to do that is y1 a corresponding input and output pair. If I shift x1 by 5 or any value, if it's time invariant, then the output is going to be shifted by the same amount. Okay? So which one here is time invariant? This guy? Yes? Okay. This is V2. This one? Yes? Good. 2. This one? Yes? Good. 2. So this is reviews. I'm going to do fast, okay? If you confused, see us. We'll knock this out. This guy? Yes? No. Okay. So this is interesting guy, right? Why is it not time invariant? This is the correct answer. Why?
Because it's going to put 2 in.
So, that's right. So, because this is the scale right here, right? What happened here is if you shift by, let's say, 5, what's the corresponding shift here? By 10. Right? So, you can show that because of this scaling here, it is not time invariant, it's time invariant. How about this one? Yeah, this is time invariant. Okay? What would be another property that we should know? Okay, whether the system has memory or not. So memory plus. Okay? Memory plus meaning that it only depends on the current information. There's no buffer in the system. Right? So it means no buffer. You cannot store anything. Which one here have no memory? This one? Yes. 3 here? This guy? No. But you have to say the previous input. This one? Yes. 3? This guy? No. Because for y1, we need x2. Right? You have to actually look ahead. This guy? No, because you need to save the previous output. Right? Because only these 2 have no memory. What will be the fourth property?
You say D is not?
D is not. Because y0, x of 0 is fine. What's y1? X of 2. So current time is 1. I have to say, look at the next example 2. So I need an advance. Right?
We have to go past,
Yeah. You cannot depend on any information. You cannot save anything. What could be the next property that we should review? Causal, very good. How do I explain causality? Okay, so the output y of n does not depend on future value. Very good. So this is useful. Watch. Why do we want this causality? It's for real-time system. Input coming in, and if you say previous output and previous input, you can output out right away. If you depend on the future input or information, you got a buffer, so there's an inherent delay right. Okay? Now this is not very useful in real life, system, because everybody can have a buffer, and as long as your application doesn't need a real-time interactive, then it doesn't matter how much you delay. Right? So things like streaming video doesn't matter. If I click on Netflix, Pirates of the Caribbean movie, I can wait with the buffer. Right? So, okay. So in terms of causality, it's not useful, but it's good to know. How about the last one, which is quite important? Oh, sorry. Which one is before? This one causal? Is it causal? Yes? So that's causal? Is causal? No. Is causal? Yes. This is the past output. Okay, what is the last property? Stable. Bounded input, bounded output, stable. This means that for every input, bounded input, my output is also bounded. This is important, right? You have this for certain input, your system might blow up. Okay? Which one here is stable? Which one? Yes? Okay. Second one? Sure? Stable. This guy? No? Why not? Square. If input, if x element is bounded, x squared is bounded. Still bounded. Give me a number that's bounded. A trillion. Trillion squared is it's bounded. It is. I can still write it out. Okay? We're not doing it's large. We're not saying anything about the growth, right? It's saying that it is bounded. It's still a number I can write down. That means it's bounded. Infinity I cannot write a number down. Oh, this guy. Fine. This is clearly bounded, right? How about this one? Yes? You sure? It's an input that this one will blow up. Yes. Which input is that? Which input is that?
Put a constant in there.
That's right. You put 1 as the input. The output is 1. Input is 1. What is the output? Go to infinity. Okay? This guy talked about. Let me pause for questions and we'll go next to the next topic. So, yes.
Explain what it is now,
Bounded, it means that for every bounded input, the output is bounded. So if I feed in a 1 to the system, what is the output? The 1, 2, 3, 4, 5, 6 to infinity. Okay, it could be to infinity. Even though my input is 1. Okay? All right. So let's talk about convolution. Yes.
Under system E, if you change the y sub n minus 1 to x sub n minus 1, then we
That's right. Later on, we'll see that this system here has a pole at 1. Okay? On unit circle. So we'll not down. So we'll talk about that later on. Alright. So among these properties, let's talk about linear and time invariant. So LTI system. The LTI system is useful because it makes life easier for us to analyze. And most of the systems that we talk in Process 1A, in this class, is LTI system. Okay? So let's set up XFN. We'll specifically impose linear time invariant to this system and show that it's now we will talk about a way to compute y for every x. Okay? So what I'm going to do next is I want to plug in the representation for XFN that we discussed before. Remember XFN, the linear combination of weighted shift as a function. Okay? So we plug into y, what do I get? Transformation of x of n, which is that summation we have here. So far, all I'm doing here is plug in the definition for x of n in terms of that function. Now the next equal sign is because of linearity. Okay? This guy here is arbitrary system. Well, we impose linear and then time invariant. Let's see what happens. Right? So if I impose linearity, can I simplify this? The input are weighted sum of all this sigma. If it's linear, what is output? Weighted sum of the corresponding output of this graph. Which means that I can move the t inside, right? The weighted sum of the corresponding output. Yes.
What does the T represent?
A mapping. Right, that map input output. Now, who's confused about this? Yes. Okay, good. Take an example, right? Before you have, let's say x of n is delta n plus 2 delta n minus 1 minus delta n minus 2. Remember that example? Right? So in this case here, you have 1, 2 minus 1 there. And the k here, take value of 0, 1, and 2. Right? Okay? What do I get? Yes, this. Right? If it's linear, what does it mean? It means that if I know this output, I can sum them together. So this equal sign is linear. This is basically the output of delta n plus 2 the output for this guy minus the 2. Right? Because linear, if I sum the signal together, it's linear, it will be sum of corresponding output for the signal. Right? And all doing here is writing in terms of summation. Is that clear? Okay. It's time invariant. Now, this is complicated because I have to know infinite number of response. Because this is arbitrary. Now I have to know infinite number of response, but those are only delta function. Right? So I'm reducing my class to infinite sequences, to infinite delta function, which is a huge improvement. Right? And now, the time invariant, I can make it even simpler. How? If I call delta n and x of n are corresponding input-output pairs, then what would be, if it's time invariant, what would be the output for a shifted impulse? It will be x of n minus k, shifted. What is that? That is h and minus k. Right? It's an output for that input. We call that x and minus k. So this is summation k, x of k, x of n minus k. If it's linear, I have to know the output of a system for infinite number of shifts. If it's linear and time invariant, all we have to do is know the response for an impulse. So this is a very important name that we call this. Impulse response. Okay? This is called impulse response. It is the response of impulse. And this response allows us to find the output for any input. For every LTI system, there's an impulse response, and that's all you have to know. That's why it's friendly, useful, easy to talk to, easy to analyze, and so on and so on. And who remember that's the name for this equation? Convolution. Basically, x of n convolved with x of n. Convolution, you can interchange the operation, right? You can go like this. So another way, x of k, x n minus k. Either way is fine. It's a simple. This could be convolution. So let me summarize and we'll take like a few minute break, okay? Here we review 5 properties of system. Those are linear, time invariant, memoryless, causal, and stable. we wanted to choose certain properties that make our life easier. And it turns out that linear and time invariant will make our life easier. How? If it's not linear, I have to know the response of infinite number of sequences. This is next event. For every next event, sinusoidal, exponential, weighted, anything, I need to know the response. So this is basically impossible. Right? If it's linear, I reduce the space of infinite number of sequences to infinite. That's the function. Right? So if it's linear, all I have to know is the response of the system for all the shifted impulses. With time invariant, all I have to know is the response of the system for one impulse. We call that this event. Any question? Okay. So let's take a short break. When you come back, we'll discuss. We'll give you a few examples of convolution. Just a refresher, I'm going to show you this before. You know, when I take this class, convolution is the hardest thing ever. Okay, because figure out how to flip and shift is very, very difficult. So we'll have an example of convolution. We have more examples in the whole book that we can actually work on, and then we'll discuss Fourier frequency, Fourier transform, so forth. Okay. And now here for those who simulate.